Hey guys, I am Ratna. I'm a staff engineer at Snap, working in Core Infra team. For the next few minutes, we will talk about a small library which we built called Snapcache, which turns Envoy into a programmable cache fabric, which works inside our service mesh. Just for a context, service mesh is what Snap built on top of Envoy and where all our compute runs under. Yeah. By end of this presentation, what my goal is, like, we all can walk away with how we build this Snapcache with a thoughtful interface with all primitives that we incorporated that works really well at Snapscale. So before I go into more details about this, first let's understand what the scale I'm talking about. Uh, Whenever a user opens a Snapchat, right, multiple recommendation systems get triggered, and they evaluate around 100 to 1,000 candidates for each request, which in turn a candidate pulls hundreds of features. What this overall means is like hundreds of millions of feature lookups is what the scale we operate on. So all these requests is going to hit cache. So at this scale, right, every recommendation system will run into multiple issues, like how do we handle the connection bloating issue? How do we handle the cache migrations, which has to happen behind the scenes without any downtime on these recommendation systems? And how do I protect my cache if there is a traffic spike for various reasons? And how do we efficiently serve this in a most performance and cost-effective way? Yeah, so all these the things which we incorporated inside the Snapcache the library, so that the teams can just use this. Yeah. So what is a Snapcache lib? It's a truly stateless async library which is built on top of Redis Envoy proxy components. What I meant by stateless is basically it doesn't store any the in-flight operations. It doesn't manage the in-flight operations. It just wraps it around a handle and returns it immediately to the caller. And the caller manages the handle, or let's say, why this is important is, let's say if the caller times out or dies while the in-flight operation is happening, they can just call the destructor of the handler, or just call the cancel that we provide, and all the logic inside the handle will be all the complex logic of how do I gracefully shut down the in-flight operations, and how do I deregister all the callbacks. Is everything, all the logic is done inside the handler. That way, this Snapcache is truly stateless, and it does not maintaining anything. And the async nature comes from the callbacks. Like a caller calls this method, it gets a handle immediately, and they register what a callback they need to do once the cache responds. And it's very simple. And the interface are designed in a cloud in the vendor agnostic manner. That way, today it's Valkey, and tomorrow if they want to plug in some other cache technology, they can easily add it. That's how we build this. Yeah. Yeah, and definitely since our interest is how on this Valkey, we didn't build. The Envoy is an open source, and it already has a Redis proxy. We leveraged those components, and we build our secret sauces that works well for our scaling and Snap requirements. Yeah. So just to go a little more, so this Snapcache library does something more. It's basically a tiered caching in a cloud agnostic manner, in a vendor agnostic manner interfaces, and it has a local cache which is built on top of Meta's cache lib, which has local RAM and SSD support. That's basically L1 cache, and anything the cache is there, we build something called Snap Remote Cache. That's what we are going to talk for the rest of the thing, and that is powered right now by Valkey, which is L2 cache. And anything the miss that any cache miss is there, we'll go and fetch from the database, which is either Dynamo or Bigtable, depending on the recommendation systems, how the recommendation system is built, and it backfills both the L1 and L2 cache. That's how this interface is. But yeah, we are mainly talking about the Valkey now. Yeah. So let's talk about the 5 pillars. The first pillar is called connection sharing. Let me talk about the problem. A recommendation system pod, of course, on that, when I say pod, basically everything in Snap is Kubernetes. So a Kubernetes pod, which an Envoy runs, has n worker threads which will be configured, and each worker threads open a connection with the Valkey server. So with this approach, right, if you have n pods, you'll have n into m connections, which to a single Valkey cluster, Valkey node. So the connections are now scaling linearly with the number of the fleet size. So this has two problems. First thing is Valkey only supports I think some 64k connections per node. After that, I mean, yeah, that's the max limit. And the second issue is, if you have more connections connecting to the node, you're burning. Basically, you're creating more sockets. Basically, you're burning the more file descriptors, which means you're burning the CPU of you're burning the Valkey node CPU just for this connection management. So how did we solve this? So we built something called connection subsetting or sharing, where we choose few cache worker threads as the cache owner threads, and the rest worker threads as forwarders, and we do the thread hopping. When a request lands on worker thread, which is a forwarder, we'll forward it to a cache worker using the Envoy's dispatcher, and once the cache worker does it, then the callback will be executed back on the original worker. So that's the thread hopping thing we do. So we ran this experiment with having one cache worker thread. Of course, that's very bad. One cache connection at this scale will queue up all the requests. So, but we found a sweet spot where we have for three cache worker threads, we could achieve the same performance, and we could reduce 80% of the connections. So this unblocked all our migrations to Valkey, and it's working well. Yeah. The second pillar here is something called cluster grouping. So what this means is, so Valkey has a limit of on a cluster size, and for our scale, we are able to hit that limit easily, either because of the traffic or mostly because of the traffic, but for some cases which are memory bound, because of the data also, we are able to hit this limit. So we build something called cluster group, where we have an array of cache instances which are static, and the ordering matters, and it's a bootstrap time we configure this, and we hash the request key uniformly across these caches, and it lands, and we use that hash to route this to one of these caches in the cluster group, and then it's basically a horizontal sharding here. And we use CRC64 here and not 16, because CRC16 is what Redis Envoy proxy library internally uses to shard a key across the slots. So we use, since we are in an Uber layer above it, we use 64 to uniformly distribute the key spaces across the clusters. And this is immutable. So if you want to change in future, hey, my scale has limit, so I want to move from a 4 cluster group to 8 cluster group, it's a cluster migration. So this is one of the reasons why we have to do cluster migrations, and these which I'll talk later. And we have to do migrations behind the scenes without the downtime. And how we do it is what I'm the next slide is. Yeah, how do we do this? So we built something called a mirroring layer, this is what this tool has. It's a multi-step tool, like, you know. So we have a concept of a primary cluster group and a mirroring cluster group. First stage is like we do a dual write, which is a fire and forget, which can be ramped up from in a stepwise. And the second stage is dual read, and the metrics to compare to make sure that the data is parity. And the third step is the inverting the primary and the mirroring. So these are the 3 stages. Currently, it's a little bit of manual. Migration is manual, but we are trying to automate this. So the cluster migrations will be seamless, automated, and yeah. The next one is something called load shedding. So for various reasons, we see traffic spikes, a huge traffic spikes, like an MLE engineer launches a feature sets, or there is an event. For various reasons, you may see a traffic spike, and when a Valkey node hits 100% CPU, or when a Valkey cluster hits 100% CPU, we it melts down. The only way, because there is no autoscaler in this case, so the only way we can protect our cache and do a recovery from there is to stop shedding, basically to shed the traffic to cache and do the operations like either scale up or anything. Otherwise, once a CPU reaches 100%, I think Valkey will be in a unrecoverable state and the requests keep queuing. So load shedding is pretty important. So we have two types. One is manual load shedding, and the second one is automatic. The manual is like an operator comes. An operator comes and manually load sheds. The other thing we have is Envoy has something called admission control, where the framework is you can monitor certain metrics and it automatically load sheds. It's a proactive load shedding. That's the other thing we do. And the metrics there are multiple ways metrics we choose. We generally monitor. We can monitor the depth of the queue is one thing. There are many metrics we can monitor to tell whether the cluster is healthy or not. And this helps us a lot to recover from various events. Yeah, traffic events. So the next, let's put all together. 1 second, sorry. I need to talk about the zonal. So zonal affinity is the other feature which we developed. So what this means is like, it's pretty simple. Like when a read comes, we have to prefer the replica that is in the local zone, because cross-zone costs in AWS or GCP is pretty costly, especially at the scale we operate. So we had to have this feature enabled inside us to save this cost. So yeah. So let's put all together. So yeah, a request comes. When it lands on a forwarder thread, it sends to cache worker thread, and then it checks whether I should load shed or not. And then it routes to the corresponding cluster in the cluster group, and then it sends to it prefers to serve from the local replica, and that's it. So what is the payoff? We could serve the recommendation. We could serve the requests at 20 milliseconds at P99. Given our budget is 500 milliseconds, so we are way better after onboarding to Valkey, and all the cache access are consolidated to one snap cache lib under Envoy. So previously there used to be each team has to have their own Redis client and do optimizations ad hoc way, but now it's all in here, and the on-call is also, of course, this consolidated. Yeah, so the key takeaways are cluster grouping, which will help you to go across the limit, scale across the limit, and you have a connection sharing feature which lets you to do the same amount of work with less number of connections, and you have a zonal affinity feature which helps you to reduce the cost, and you have a migration tool which migrates caches behind the scenes without a downtime. That's it.